Let me ask you a question. Let's say we have three resistors and they are all connected in a series to a battery. This is our battery. These are our resistors, all connected in series. Now, if I know that the current flowing through R2, which is the middle resistor, is 2 amperes, then what can I say about the current flowing through the first and the third resistor? Right? I'm aware of the current flowing through R2, but now I need to find out the current flowing through the first and the third resistor. Now let me just confuse you a little. Let me just ask, so the question is clear, right? We want to find out the current in R1 and R3, but now I'm trying to confuse you a little. I'm trying to give you some more information about the circuit. And the information is that the first resistor has the highest resistance, while the third has the lowest resistance, right? So if you know this, if you know that R1 is greater than R2 and R2 is greater than R3, and if you also know that IR2 is equal to 2 ampere, can you find out the current flowing through R3 and R1? Now you might be thinking that should the current be lower in the resistor with the highest resistance? And this makes sense because higher resistance should make it harder for the current to flow, right? If higher resistance, then the current should be lower. It seems like a valid idea. Or you might be thinking that if the electrons are the ones which are carrying the energy, then they should lose energy, right? As they supply this energy to the load. Because these are the ones who are carrying energy. If that is the case, then as they supply it to the load, they should lose it. And they should cause them to slow down and reduce the current. And by the way, this is a very common idea that if the electrons are energy carriers, then the electron should slow down. And ultimately that should result into lower current, right? So progressively the current should reduce. But let's see if that is the case. And there is another very interesting idea which many times my students would discuss with me, and which is that is it possible that the source of energy is the charge itself? Could the load consume some of the charge, reducing the current as it flows through the circuit? Because current is ultimately how much charge is passing through a cross section per unit time. If the charge itself reduces, then the current should reduce, right? So is it the case that the load is actually consuming some of the charge? So these are all valid initial thoughts. And what we are trying to do over here is that we are trying to model how electrons flow inside a series circuit using whatever we know about energy and the components of a circuit. But it turns out that all what we have thought so far is not correct. Because all these models would predict outcomes that we do not see in the real world. That's very important. These are what are we doing? We are modeling. We are trying to figure out what is the nature of reality. But whatever hypothesis we have or whatever ideas we have, when we try to use those ideas to predict some outcomes, and if we see that we are not able to predict what actually happens in the real world, then that ultimately tells us that something is wrong about our models. So today let's explore why these ideas do not fully explain how current behaves in a series circuit, and let us also figure out the model that does explain in the behavior of current in the series circuit so that we can find out the answer to our original question, which is what is the current that flows in R3 and what is the current that flows in R1. Let's just first discuss our initial thought that higher resistances should lead to lower current. While higher resistance does oppose the flow of current, but it does not necessarily mean that the current itself decreases. So higher resistance will create an imbalance. But this imbalance would be for a very, very small amount of time. What does that mean? That means that there will be a transient stage. There will be a transient state where the current might be slightly different in different sections. So it is likely that these three sections might have different currents flowing through them for that transient state. But that transient state, as the name suggests, is going to be very brief. So this imbalance, this imbalance quickly corrects itself. This is because different rates of charge flow will make the charge accumulate. What does that mean? That means that this imbalance crucially would ensure that there would be an imbalance in charge density, and it would lead to a stronger electric field within the higher resistance region. And it is this stronger electric field which would accelerate now the electrons moving through the higher resistance section. So what we are trying to say is that because of this imbalance over here and over here and over here, what we are seeing is that there is now a stronger electric field as well. So the electrons now are actually moving a little faster just to compensate for the lower charge density, which could be the reason behind the higher resistance. And that ensures that the amount of charge that passes at any point in the circuit per unit time remains constant. Let us also think about this other idea of charge being consumed by the load. Because it could be a belief, and that is what we discussed earlier as well, that since a few of us have this notion that charge is the source of energy, so the components of the circuit must be consuming it. However, this idea is also incorrect. And the reason is that the charge is always conserved. The total amount of charge entering the circuit must equal the amount leaving it. And what does that mean? That means that the load is not using up the electrons. Yes, the movement of electrons does enable the load to utilize the energy of the battery. But this is happening without consuming the electrons. It still appears that the electrons are the energy carriers. And it's a common misconception that electrons themselves carry energy like tiny batteries. While electrons are essential for current flow, they do not directly transport energy. The true energy carriers are electromagnetic fields. When the battery is connected, it establishes an electric field within the circuit. As electrons move under the influence of this field, they generate a magnetic field. Interplay between this electric and magnetic field is what creates electromagnetic waves. And these waves, when they propagate through the circuit at nearly the speed of light, transfers energy to the load. And this is how you explain how energy is transferred in a circuit at the speed of light, which is much faster than the slow drift velocity of electrons. So in summary, all our initial thoughts which made us predict that the current would be different in different sections had some conceptual inaccuracies. We had some misconceptions. We initially thought that charge might get used up in the circuit, but that cannot be the case because charge is always conserved. We also thought that perhaps because of the variations in the resistance, there would be differences in the current in different sections of the circuit. But initially, there could be some transient states. However, these transient states are quickly resolved by adjustment in charge density and electric field strength. The system dynamically adjusts to maintain a steady flow of charge, ensuring that same amount of charge passes any point in circuit per unit time. And we also thought that perhaps electrons are the ones which are carrying energy and hence they should slow down and hence the current should reduce. But that also is not the case because energy is carried by the fields. So the answer to our initial question is that the current through all the resistors is same. It is 2 amperes.